we fill so we fill this area with a dielectric. Then what that actually does is that means that there's a bunch of random molecules all inside this dielectric. However, when this system becomes charged and an electric field is placed between the plates, in a dielectric, the polarization of the molecules helps those molecules align with the applied electric field, which means these random molecules will attempt to line up in such a way that their negative side and their positive side will align with the field. But when all of their molecules do this inside a dielectric, you can imagine that the charge of the particles inside the dielectric enhance the field, creating a stronger field than would be there without the dielectric. So if you're asked about what's happening inside a dielectric, you should mention three things, three specific things. That the molecules of the dielectric are polarized, meaning they have a positive and a negative end. Those molecules align with the applied electric field. And the molecule's electric field adds to the applied electric field. Those three things should be discussed. That connects all the dots to tell you what a dielectric is doing between the plates of a capacitor. However, we have no such dielectric here. So, and by the way, I'm going over this. Did you guys work these out? If you want, did you upload it so that I can show that you tried tried to practice these? Because if I'm just going to go over them, it'd be nice if you got credit for having done some of the work yourself, right or wrong. If you want a minute to just upload it real quick before I go over it, so I can give you credit for making a reasonable attempt. It's not due this minute. I said end of the day. But if I go over it, I expect everybody's to be perfect after this. Alex has his hand up. He's had it up for a while. I'm talking right over the top of him. But let's see what Alex has to say.
I just want you to repeat the three things that you want us to say when describing.
Alex wants me to repeat myself. It hurts my heart to repeat myself. Okay, Alex, here you go. 1, the dielectric has polarized molecules, which means they have a positive and a negative end. Thing 2, those polarized molecules align themselves with the applied electric field. Thing 3, the molecule's electric field, therefore, adds to the applied electric field, enhances the applied electric field. I'd say magnifies, but that's the wrong word to use there. Enhance is a better word. Adds to is a simpler word. We good? Okay. All right, we good to go? Let's do it. Determine the electric field between the plates. Okay, so hopefully this wasn't too bad, the electric field between the plates. So you're just going to use a couple of things we already talked about yesterday. So I kind of did that purposely yesterday so we could have these things to talk about. The electric field between the plates is going to be the electric potential divided by the distance between the plates. We have an electric potential V applied between the plates, and the distance that we're supposed to use is this B. So I'm going to say that it's V over B. That's it. What's that? So you're saying the formula sheet is this, right?
No, I'm saying the formula sheet is E equals negative dV over dx.
Okay. The negative sign for that. And I'm being asked by Max, why is it not negative? So he's using from the equation sheet this formula. which is a reasonable thing to use. So don't for a moment think this is an unreasonable thing to use. There's three things here that I would point out to help us. First, this suggests two things. First, that we can be finding the electric field for any expression for the potential that's in terms of position. It allows us to determine what the electric field is for any expression. We have an electric field that we know is constant because it's between the plates of a parallel plate capacitor. The negative sign there is to help us indicate whether the electric field is positive or negative. And for a parallel plate capacitor, that's a little bit of an ambiguous decision. And I don't mean ambiguous as in we can't figure it out. We have the battery, which tells us clearly what side of the battery is positive and negative, meaning we know the electric field is going to be this direction based on the way in which it's connected to our potential difference. But I'm trying to determine whether it matters to give the direction here. And it probably does. But I'm sure that if we went to the solution guide, it wouldn't say negative V over B. It would just be V over B because it's determining the size of the field between the plates. The negative sign would help us indicate whether the direction we're facing is going to be going up a potential or down potential. And I know that's what this negative sign is about, helping us determine the direction of that electric field relative to the change in potential of dx. So, it's telling us that the electric field opposes an increase in potential over a distance. So I like to use the uphill and downhill thing to say that if you're going uphill, that would suggest the field would be downhill. Like going up potential, the field would be against the direction you're moving. So I don't know that that is applicable here unless they needed us to know which of the plates was positive and which was negative, which they didn't ask. But I don't know that you would be marked wrong for writing negative V over B, as you would be pulling it right off the equation sheet.
And also, the bottom one would be negative. So it would be safe to say that negative V would be kind of be right. The electric field is the arrows would be pointing down.
Well, the arrow's pointed downward, yeah, because the electric field leaves positive and goes towards a negative. So, like I said, it just said determine the electric field between the plates, which we know to be a constant. It would probably be better to say that the electric field is, based on the picture, downwards rather than negative V over B. But my experience has been with these kinds of problems related specifically to circuit and circuit elements, that direction of electric field only needs to come up in your answer when asked. That we generally don't care about the direction of the electric field between the plates. We care about what that energy can do when used elsewhere. Now, there will be a time, I'm sure, when I will be proved a liar and it'll come up, like probably the next FRQ. But this one I don't think will matter. Question B, determine the charge stored on each capacitor plate. Now, the charge stored here, I don't think is a big issue either, because we have information we can use to determine what the capacitance is. So for question B, we know that the definition of capacitor is Q over V. We're allowed to have V in our answer, but we're probably not allowed to have C in our answer. But we're allowed to put an expression for C in terms of what we've been given, which is epsilon naught A over B equals Q over V. So I think we could express Q in terms of the given variables here, which would be Q is equal to V epsilon naught A over B, which is behind my head, so you can't see it anyways. All right, so far? Questions about this one yet? Question C? A copper slab, the word slab shows up on the exam a lot more frequently than you would really be surprised to see. I don't know why, but they have lots of slabs. whether it's in the E&M test or the mechanics test. A copper slab of thickness A is now inserted midway between the plates as shown below. Determine the electric field in the spaces above and below the slab and determine the ratio of the capacitance with copper to without copper. I think that there's a number of ways we could approach this problem, and it would be right no matter which way we approached it. I would like to approach the problem by not leaving the copper in the middle and recognizing that it doesn't matter whether the copper's in the middle and creates two separate capacitors, or we move the copper to the bottom and just have one capacitor. Do you understand what I'm suggesting? So I would kind of like, I think it'd be easier for us just to think of this as that's my capacitor, where I've just slid the plate, slid it to the bottom, and this is the distance B minus A. And that becomes my new distance between the plates. The electric potential hasn't changed. The electric potential is still V. I've just effectively reduced the distance between the plates with the same electric potential. So it says determine the electric field in the spaces above and below the slab. Electric field is going to be whatever this works out to be. So that's going to be because we know there's no electric field inside the copper. Now, we could do this different. We could look at the spaces separately and break this up into two capacitors and all that kind of stuff and look at the partial electric potentials. But knowing that that has to be true seems like this is the right way to go. Would you like to look at it a different way with the copper plate placed in the middle? Okay. So we're going to place the copper plate in the middle. Now, in doing that, it changes what we have to do a little bit. So let's draw this a little different. So this is A now. And so this has to be B minus A over 2. And this area has to be B minus A over 2 as well. Okay? Any question about that? So I'm going to go here to figure out the electric field and integrate. Not because I think I have to, but because I think it's the way I would do this if I was being asked to do it. Now, it's not really going to be an integral because we know what the electric potential is from here to here. What we're really doing is finding the electric potential from here to here, the electric potential from here to here, and the electric potential from here to here, and then adding them all up. We know the total electric potential has to be V. And that's going to be broken up into 3 integrals from, let's just label this 1, 2, 2, and 3. Well, no, you guys won't like that. Let's go 1 to 2, 2 to 3, and 3 to 4. So my electric potential will be the integral from 1 to 2 of E dot dx plus the integral from 2 to 3 of E dot dx plus the integral from 3 to 4 of E dot dx. Now I'm going to get the electric field from this. I know the electric field in here and in here have to be the same, or at least have to be a constant. But positioned the way it's been positioned, they'd have to be the same because of the symmetry. So that's going to be E times B minus A over 2, because that's the distance, plus 0 times A, because the electric field inside a conductor has to be 0, plus E times B minus A over 2. So I've broken it up into 3 parts. The electric potential is what was applied. So this is going to be E times B minus A equals V, or E equals V over B minus A. So that's probably how I would do it if I was trying to explain it. Okay? Determine the ratio of the capacitances of C with copper when the slab is inserted versus the original. Okay. There's probably more than one way to do this, but I think we effectively have either 2 capacitors and we look at the total equivalent capacitance, or we just realize it's 1 capacitor with less space. Which one would you guys like to do? 2 separate capacitors, we look at the equivalence, or 1 capacitor with less space? Okay. We do the capacitor with less space. We have the added benefit that it's a little easier to do because we have the capacitor with copper. It's going to be epsilon naught A over B, and I'm sorry, not B, B minus A. And the capacitor without is just epsilon naught A over B. And we're looking for the ratio. So the ratio is going to be B over B minus A. Maybe. Is it? I don't think so. It's with copper to copper, right? Or with copper to original. So yeah, no, that'll be it. We know that the capacitance has got to go up. So I expect this to be a number that is greater than 1, because effectively we have a capacitor of the same area with less distance between the plates. So I think the ratio should be a number greater than 1, and this way it is. All right. I'm okay with this question. I think it's all right. I'd love to see this on the exam. I don't think there's a whole lot here. Modern exams, they've had questions kind of like this, but this is a pretty old problem. This is, back in the 70s or early 80s. It's not this one that you guys really want to know about, though, is it? It's this other one. This one?
Okay. On D, from the last one, wouldn't there be a K with the width?
Wouldn't there be a what?
K for the dielectric.
There's no dielectric in it.
The copper?
Copper doesn't count as a dielectric. There's no electric field inside the copper, so it can't be a dielectric. It's a conductor.
Okay, that makes more sense.
All right, so this one's just, I think, a kind of a weird kind of question. So let's, I don't know, we'll put me back in the corner, I guess. Nobody puts baby in a corner, but I put myself there, so it's okay. All right, 2 large parallel conducting plates are joined by a wire as shown above, so that they are at the same potential. Okay, that's important. We have put them at the same potential, so there's no potential difference between the 2 plates, the top and bottom. Where was I? Between the plates at a distance A from the upper plate and a distance B from the lower plate is a thin, uniformly charged sheet whose charge per unit area is sigma. The electric fields between the plates above and below the sheet have magnitudes E1 and E2 respectively. All right, so let's write that down because that sounds like something I can use. E1 and E2. And based on what I'm seeing here, E1 is probably greater than E2 based on the picture. But that's likely to do with the fact that A is smaller than B based on the picture. Determine the ratio of E1 to E2 so that the potential difference between the outer plates is 0. Okay, well, I think what that really means is that the potential to here, V, and the potential to here, V, are opposites. So that when I go from here all the way to here, I have a net change of potential of 0. So I increase my potential going from the bottom plate to the middle. And then I decrease my potential going back out to the top. Everybody understand what I'm saying there? It has to be that way because the charge separation is clear. They put that the middle piece of aluminum has positive sigma, and both of my up and bottom plates have, they say negative sigma 1, negative sigma 2. So, but the middle one is just negative, it's just sigma. But if I want, I can say that this is V2 and V1. If I don't believe they're equal, that's fine. But I know that negative V1 plus V2 has to equal 0. And I'm putting a negative there because of the direction of the electric field relative to the plates. If I'm going from the bottom plate to the top, I am increasing potential going from bottom plate to middle, and I'm decreasing potential going from middle plate to bottom. Is that okay so far? Well, based on that, V1's got to be E1 over A, and is negative. And V2 has to be E2 over B. And that has the sum to be 0. We doing okay so far? Anything weird I'm saying? All righty. That's good. Then I just need to get E1 to E2. So it looks to me like I can set those two things equal to each other. So E1 over A equals E2 over B. Do a little cross multiplication. I get E1 over E2 equals A over B. Woohoo! That's A. How are we doing? Matt made this face. I'm sorry, Max made this face. You all right there, Max? What happened? You put, what do you mean for 1? Yeah, I don't think so. Okay. But what's funny though is it looks like we did it all correct. It looks like it's all set up correct. But the way they drew the arrows doesn't seem to jive with what we have here. Do you guys understand what I'm saying? Because from what I'm seeing, we made a mistake. Sorry, I say we. I made a mistake. Today is November 17th. It is 11:05. You should write this down. Alex, you keeping track?
We'll celebrate this day each year.
Yeah, I made a mistake. Potential equals E times D. I was trying to figure out why the electric field was stronger in the area where the plates were further away, and that didn't make any sense. So I should have written this as minus E1 times A plus E2 times B equals 0. And instead, I didn't do that. I put them over each other thinking, I don't know what. So this is, I think, what we're supposed to do. I am sorry. Okay? That's going to make a difference in our answer. But it's going to make the answer what I think it's supposed to be, which is E1 over E2 is going to be B over A, which makes more sense. Now it shows the electric field is stronger in the area where the plates are closer together. And that's what I would want to see. So there. Michelle made a mistake. You should expect more of your teachers. Let's go on to question B. Maybe I'll make a mistake here. The Gaussian surface in the diagram immediately below has faces of area A parallel to the charge sheet. By applying Gauss's law to this surface, develop a relationship among E1, E2, A, and any fundamental constants. All right. By applying Gauss's law, I have to use both the top surface and the bottom surface of the plate. I'm assuming that I have to use that this is my entire area. So the whole thing, something like that. And that's not a great drawing. Let me zoom in on this. Not that you could do this as easily as I can, but if we zoom in on it, would you agree that we're only going to have flux through this top surface and the bottom surface that's the same? And there'll be no flux anywhere else. Is everybody okay with that? So, and they're going to be positive flux on both surfaces. Is everybody okay with that too? Because electric field is going up through the top surface and down through the bottom surface. Everybody good there? So when I think of flux for the top and flux for the bottom and flux for the sides, that all has to equal the Q enclosed. And there's got to be an epsilon here someplace, epsilon naught. Is everything okay with that? And this is 0. Q enclosed is going to be sigma A. Flux for the top is going to be, is not going to be E1A. And flux for the bottom, E2A. I don't know what they're driving at with this problem, which is why I gave it to us. It seems weird. But this seems like our answer is going to be epsilon naught times E1 plus E2 equals sigma. All the A's go away, which I would kind of expect since it's a Gaussian surface, and usually the size of the Gaussian surface doesn't always stick around. Well, that's it. Fundamental constants, charge, kind of done. Keep going. Go ahead, Max. No. Ask. Look, this is a weird question. This is why I gave it. Let's get it out. What do you think?
I just didn't, I mean, when it asks for a relationship, I assumed that then, okay, so first of all, this is where I got the wrong answer from, part of it.
Okay.
Because they're both going to be the same.
What's both going to be the same?
If you use that, they're both going to be sigma over 2 epsilon naught
For
the electric fields for that.
well, I don't know that E1 and E2 are the same. In fact, I think that we have evidence that they're not the same.
Well, yes, that's the problem.
Can never trust the picture. Oh, I know, but like I say, you can never trust the picture. So we don't trust the picture. They might be leading us astray. But
Teachers and students, please pardon this interruption. Students that are testing this afternoon, you should have received your pass in third period. Third period teachers, if you haven't completed your classes yet, please do so at this time. Those students, you will.
we had a long conversation about this morning.
Again, all
During
students
first
that are
period, they
testing
told
this
us all of
afternoon
these things.
will go to
Why do
lunch
they have to
break
tell us
and
again?
report to your
Why?
testing location for
Are we
lunch.
stupid?
Thank you.
So what you guys at home can't hear is that Max and I are kind of having a conversation about what to do here. He used this earlier to indicate that he thought maybe E1 and E2 were the same. And then a few folks have indicated, well, the picture suggests that the two electric fields aren't the same. The first thing I want you all to know at home is we can't count on anything about a picture. So don't ever trust a picture to be telling you or communicating anything unless they clearly indicate it on the picture. Like we can take that A and B are not the same size, but the fact that they put the extra arrows in there and the other arrows on the bottom Don't assume that that's telling you that there's the electric fields there. We are being asked a lot about questions about the electric field. So I don't think you can count on them being different. However, we know the electric potential had to be 0 from the bottom plate to the top plate. And with that knowledge, we know that these sums had to be the same. And that tells us that E1 and E2 are not the same unless B and A are the same. So we know E1 and E2 have to be different. They have to be. Now, I don't know where this is going, but I bet it's going to have something to do with sigma 1 and sigma 2 here in a minute. That's my guess, is there's a reason why they labeled these sigma 1 and sigma 2. And I bet we're going to be finding something about the 2 charges. That, in fact, I've done this before. So, C, by applying Gauss's law to an appropriately chosen Gaussian surface, show that the sum of the induced charge density, sigma 1 and sigma 2, on the inner surfaces of the conducting plates equals negative sigma, and indicate clearly on the diagram below the Gaussian surface you used.
Well, I guess not.
Which Gaussian surface would you guys use? A star? I'm thinking, oops, let me get one that's not opaque. And just bear with me. I think this Gaussian surface. If I use this Gaussian surface, I'm inside 2 conductors. So actually, I guess I'd want the Gaussian surface to be a little bit smaller. Here and here. Because effectively, the electric field here has to be 0. The electric field here has to be 0. I'm inside conductors. And the electric field, the dot product on the sides has to yield a flux of 0 on both of these, which gives me a net flux of 0. So the total enclosed charge has to be 0. That's what gives me that sigma 1 and sigma 2 have to sum with sigma to give us 0. Because I'm enclosing the plate with a charge of sigma. Obviously, we're going to need more time on this tomorrow. So, bye, guys. But I am pointing out, I just did what Alex